Dragsters, different to drag queens, but equally amazing. Dragsters are designed to travel short distances very quickly. Okay, so that might be a distinguishing factor. I don't know. If you don't know what a dragster looks like, it's talking about the car. Well, it's talking about the dragster. And so, not to scale, something like that. A very flat, very high-powered car with a massive engine. Right, and they go for drag races to travel short distance very quickly. We're given a speed time graph for a dragster, so let's assume that this is a drag race, and it takes them 16 seconds. However, we don't know when the race starts or finishes. They might get a run-up, or they might have some time to decelerate afterwards. But so let's explore that now. So for a speed time graph, it's traveling at a constant speed when the speed time graph is flat. It's horizontal. So for example, up here, it's traveling at a constant speed of 200 meters per second. Whereas in this first section, the speed is changing, right? It's increasing, and it's over a certain time. So we can work out its acceleration, change in speed over time. So question A, what is the maximum speed? Well, that will be the greatest value on the speed axis. In this case, that would actually be 200 meters per second. Right, so this dragster has a top speed of 200 meters per second, and that's between 4 and 6 seconds. Part B, using the graph, show the acceleration of the dragster in the first 4 seconds is equal to 50 meters per second squared. So it's a show that question, so we need to show a calculation. But I like these ones because they've given us the answer, so we can check our answer straight away. And if we're not right, we just try something else. So for a speed time graph, acceleration is equal to the change in speed over the change in time. And so for us, the change in speed goes from 0 up to 200 meters per second. So the change in speed would just be 200, or 200 minus 0. And the time it takes it to reach that speed is 4 seconds. So 200 divided by 4. Which does indeed equal 50 meters per second squared. So we'll save the marker some time, give ourselves a tick. Don't actually do that. Well, maybe. All right, so we've showed that that acceleration is 50 meters per second squared, which is about 5 Gs, right? 1 G is an acceleration of 10 meters per second squared. So this thing's accelerating very quickly. We're given the mass of the dragster, so about 1 ton, 1050 kgs. What is the force required to accelerate the dragster? It should be 250 meters per second squared. So force required to accelerate it. We know Newton's second law. The net force is equal to the mass of an object times how quickly it's accelerating. And we're looking for the net force, so we need to substitute in the mass and the acceleration. So net force is mass times acceleration. In this case, mass is 1050 kgs, and the acceleration is 50 meters per second squared, to give us a net force of 52,500 newtons. So remember, net force isn't the force in the direction of, let's say, the thrust. It's that force minus the force of friction. It's the net force. After you add up all the forces, this is how much force is in the direction that it's accelerating. All right, that leads nicely on. Oh, who drew this? What a beautiful drawing. So NZQA sometimes takes away the images for, copyright reasons and things. So I've given us some beautiful dragsters here. So on this diagram, draw and label arrows to show the size and direction of the vertical and horizontal forces as it accelerates. So that's in section 8. So a free body diagram. So let's start with the vertical forces, because they're often, well, not always, but can be easier, especially if it's something that's on the ground. So assuming the dragster isn't flying, it'll have a weight force. So F weight. And to prevent it from flying, this prevents it from flying, but to prevent it from going through the ground, it will have a normal force, or a reaction force, sometimes called. Yeah, let's use reaction. Normal just means it's perpendicular to the ground. Let's say reaction force. And these two forces will be equal. Right? They'll be equal, which tells us it's not accelerating vertically, or falling through the ground or flying. So those would be our vertical forces. Our horizontal forces, since it's accelerating, it's going to need a thrust force. Let me just take these from the gray box. It's going to need a thrust force, right? And that comes from the engine. So F thrust, or F engine. And now, how does this arrow compare to the drag force? So right, it's moving pretty quick, so there's going to be a decent amount of friction or drag. However, since we know it's accelerating to the right, we know that there's a net force to the right, which tells us that the thrust force is greater, that's not a horizontal line, than the drag force, or the friction force. Right, so the thrust force is greater than, or much greater in this case, than the drag force. Right, so just to summarize this free body diagram, the vertical forces are equal and opposite, so the weight force and the reaction force, because it's not flying. The horizontal forces are unbalanced, right? There's a net force to the right because it's accelerating, so the thrust force is greater than the frictional force, or the force due to drag. Next question. All right, what about in section C? So it's decelerating. Okay, so let's remind ourselves, what does that look like? So we just did section A. Section C, decelerating. So it'll look similar, except the net force will now be to the left, right? Because it's not accelerating forwards, it's actually changing its speed to decelerate. So we'll have the same vertical forces, so the reaction force, the weight force, right? And let's assume the mass didn't change. Like technically, right, it would have burnt a bit of petrol, but kind of insignificant in that short amount of time. Vertical force is done. It's still going to have a thrust force, but actually it'll be less than in the first part, won't it? Because they would have taken their foot off the gas and maybe even started applying their brakes. So I'm going to draw that a bit smaller. And in some cases, you'd be correct if you just didn't even draw this, because we're just assuming it still has a thrust force. But it's hard to tell. or it could actually be the same length as before, but we've just applied the brakes now. So again, this bit's a bit up to interpretation, but what we do know is that the frictional force, so either due to drag or the brakes, is a lot greater than the thrust force. And that will cause it to be unbalanced, and there'd be a net force to the left, which means it would be decelerating. Oh, it's using a parachute. And no, it's not falling from the sky. It's not falling down and using a parachute. That's not a parachute. What is that? Right, it deploys it behind it to slow it down horizontally, in case you didn't get that, which I'm sure you did. So compare the size and direction of the net force in section A with section C. Okay, so we're just given the graph again, and we're just asked to compare them. All right, so direction of the net force. Well, from the previous two questions, we said in section A, net force is to the right as it's accelerating, and in section C, since it's decelerating, net force is to the left. Right, assuming the dragster is moving to the right. All right, so we've already compared the direction. We'll put it into words in a second. Direction was done. So they're in opposite directions. Like this one is forward, let's say, and this one is backwards, the net force direction. What about the size? So the size of the net force, remember, is equal to mass times acceleration. In section A, since this is the speed time graph, the gradient is steeper, and we know acceleration is actually equal to the gradient, right? Change in speed over change in time. So steeper gradient. So we'd say the acceleration is greater, which means the net force is also greater. The size of the net force in section A is greater than in section B. Excuse me, in section C. Because the acceleration is greater, because the speed time graph shows us that gradient. All right, let's try put all that into a few sentences. All right, if you haven't already, do try that yourself before you watch the rest of this or check the solutions. All right, so just write down a few ideas. So the slope or the gradient, section A, is steeper than section B. This means there is a higher or greater acceleration in section A than there is a deceleration in section B. Similarly, section A has a higher net force, as we know the net force is equal to mass times acceleration, and we've just said the size of the acceleration is greater in section A. The direction of the net force in section A is forward, as it is accelerating. Whereas the direction of the net force in section B is backwards, as it is decelerating. Full stop. Whew. So just to summarize that, we talked about the slope, right? The gradient of the speed time graph and how that relates to acceleration. We then link that to the net force, right? Because net force is equal to mass times acceleration, we know that section A will have a greater size of its net force. And we then commented on the direction, the relative direction, right? I didn't say right or left because the question didn't say it's moving to the right. So I just said forward and backward to justify that. Awesome. Well, we finished that question in a lot longer than it takes to complete a drag race, but we're done.